Should I be close to this? Or?
No, you don't have to be too close.
Yeah.
As long as you're within the range, it should pick you up.
Okay.
All right. All right. Whenever you're ready.
Yeah, I'm ready.
All right. Well, thank you, everybody. I know there's quite a few people out on the Zoom link here. Today we have Dr. Majumder. He's an assistant professor from the Department of Mathematics at University of Nebraska, Omaha. He teaches both statistics and data science courses, and he received his Bachelor of Science and Master of Science in Statistics from the University of Dhaka, as well as a Master of Arts in Statistics from Ball State University. And then following work at Ball State, he went on to complete his PhD in Statistics from Iowa State University. He has over 14 publications, and his expertise includes exploratory data analysis, data visualization, visual inference, statistical modeling, and data science. And we would just ask for people to hold off on questions until the end of the presentation, and we'll open up at that time for questions. Oh, and please mute your microphones. Thanks.
Okay, so thanks for the nice introduction. I'm very happy to be here. Actually, once I joined UNO, I tried to reach people from around the town, and I'm very happy that I could come here and meet you in here and share my ideas of the research. And I believe these ideas will be very applicable in your research area as well. So let's have fun. Even though you introduced me as a statistician, you will see that my presentation will not be that much mathematical, or it should be very intuitive, should be very convenient for everyone to follow. Okay. Now, the research is about how to use data plots in decision-making process. We know that a picture is worth 1,000 words, right? We all the time we heard about that. And this picture does say thousands of words of the life cycle of an insect, right? I mean, if I would not show you this picture, I have to explain a lot. But now, by looking at the picture, you can see that how the life cycle goes, right? I mean, during summer, they come out, and then they eat the leaves, and then when they go down to the earth, and then how the life cycle goes on. I mean, you can write a huge story out of this picture. But this picture is very intuitive. It easily demonstrates the whole activities, whole life cycles. Okay, so this is the power of picture. And we statisticians and other scientists always use pictures to deliver messages. So that has been done so far. Now, the burning question is, can we use those pictures to help us making decisions? So if we look back, where do we use pictures? We use pictures to show some phenomenon, right? To describe some pattern in the data. Now, that has been done for many years. I mean, pictures are good to do that. But we are talking about something different. Can we use pictures to make decisions, okay? To find the significance of any decisions? Can we do that? So that is the question. Before I go to answer that question, I would like to show you another picture. So this picture shows the pharmacokinetics of remifentanil. So remifentanil is a sedative medication that is administered through the bloodstream of the patient. The x-axis here shows the time. Okay? So when the medication is administered, then you can see the concentration is going up, and over time the concentration is going down. As time passes, the medication is passing out through the body over time. Okay. So the color, so each line here represents one patient, and the color represents male and female participants. Now, I may ask you one question here. There are 35 lines in each plot. In each plot, there are 35 lines. Now, looking at those plots, I have like 20 plots in here. Can you tell me which plots is most different from the rest of the plots? You can give me the number. Which plot appears to be most different from the rest? Number 4. Anyone else? You need more time. Okay, so if you choose this plot, then I would say these 3 plots all look very similar, right? This plot and maybe this plot is very similar. So they are not very different. But if we choose 4, then there is no other plot like 4, right? Look at 4 and see if there is any other plot which looks like 4, right? You pick any other plot, there will be another one that is very close to that plot. But number 4 is very different. And we have one person who could identify that, right? So what is this in here? Our hypothesis is that the pharmacokinetics of remifentanil, this medication, works differently between female and male patient. Okay, that's our hypothesis that we want to achieve. So our null says there is no difference, right? Our null hypothesis is there is no difference. Now, how do you test that hypothesis in a statistical scenario? I mean, there is no simple way to test that. I mean, I can test the difference in mean, but that doesn't make sense. As you can see, mean does not tell everything about the pharmacokinetics of that medication, right? I mean, mean is somewhere here. If you look, mean and female, mean of male and female are very similar. Mean is somewhere here, but you can see the pharmacokinetics is different. Now, to test this hypothesis, it is very tough. There is no method available to test that, right? But in that scenario, we are able to test that and we can make a decision that the pharmacokinetics is different between male and female.
Hi, Amy. Don again. Sorry to bother you. I'm not nagging, just trying to follow through. I'll be in the office here till 1 o'clock or so. Bye-bye.
Okay. Is there any problem? No. Okay. So we will decide on this, and I will let you know at the end of this presentation how we will make that decision from this plot. Okay. So this is very similar to the kind of plots that we see in the police lineup. So how many of you are aware of police lineup? No, I know you'd have to go through that, but you are aware that police use that lineup system to make decisions, right? So what happens? Police capture a suspect, right? The suspect is innocent until proven guilty, right? So null hypothesis is true. When police suspect someone, null hypothesis is true that the person is innocent, no guilty, okay? Now, that suspect is put in the cloud of several other peoples, and those other peoples are taken from the assumption that that null hypothesis is true, right? Because those other people that police know for sure that is not related to that crime. Like they're like other police officers. They put them in there. So they know for sure that other people in that lineup are coming from the null hypothesis. Only suspect is the one we don't know whether that person is coming from the null hypothesis or not. Then police come and ask you as a witness, right? Can you determine which person you think is the suspect? Okay. Now, what happens if witness can identify the suspect? What happens? What does police do? Police rejects the null hypothesis, right? Police says, okay, since witness identified the suspect among the cloud of null people, that means we have to reject the null hypothesis. That means that suggests that this suspect maybe is related to this crime. Same idea here, that in my plot in here that I showed you, I have 19 other plots that I have generated. Those 19 plots are generated based on the hypothesis that the pharmacokinetics are same for male and female. And then we plotted those 19 plots, and on the one of the plot is our observed data, which is number 4. And we have a witness who identified that it is different from the null, right? So that tells us that we can now make a decision, hey, we should reject the null hypothesis. This is an evidence in favor of rejection. Okay, so this is this kind of plot. So based on that police lineup, so this kind of plot we call it lineup plot. Okay, so this is called a lineup plot. So what does a lineup plot mean? It is a collection of plot. One of the plot is the observed plot that comes from our observed data. And rest of the remaining plots are generated based on the hypothesis that the null hypothesis is true. So when null hypothesis is true, we can simulate, because we now know the null, right? So then we can simulate those plot. Now this is introduced by Booya in 2009, and later this has been improved upon a lot, and we also worked on this area and published some paper to improve the methodology. Now, this lineup plot is then shown to some people. And then once that person can identify the plot in there, which is very different from rest of them, then this is considered to be an evidence against the null hypothesis. So here is an example. Our null hypothesis that says that slope is 0. There is no slope. Slope is 0. An alternative hypothesis is, no, there is some slope. Okay? So you can see that all of you could identify the observed plot, which is 19. And look at the null plots. This is how null plots should look like when slope is 0, right? So we generated 19 plot, assuming null hypothesis is true, slope is 0. And then we put our observed data randomly somewhere so that it is lost. And then if you could identify that, then it is an evidence against the null. Okay? That's the idea. This is the lineup plot. Now let us see how these procedures are different from our conventional hypothesis test. So I assume you are aware of hypothesis test, right? Here we have a simple linear model where slope is beta. Our null hypothesis is that slope is 0. Alternative hypothesis is that no, slope is not 0. So this is our conventional inference. And then what we do here is we estimate this slope parameter, we divide it by its standard error, and then we get that ratio, and we compare that ratio with theoretical t-distribution, right? And this is theoretical t-distribution, and then this ratio falls in the extreme tail of the t-distribution. Then we say, since it falls in the extreme tail of the t-distribution, reject the hypothesis. That's our conventional testing procedure, right? Now let's see how it compares to the visual inference. Okay? Hypothesis is same. Now, our test statistic is not just a ratio anymore. In conventional hypothesis, test statistic is a number, is a real number. But in our hypothesis, it is not a real number. It is a plot. Now, this is how we choose test statistic to test something in real life, right? We choose test statistics so that it reflects a pattern when alternative hypothesis is true, right? That's what the power of test statistic. I mean, test statistic is something that will show some big value if null is not true, right? Same thing in here. We choose a picture to be our test statistic if alternative hypothesis is true or null is not true, then test statistic should show me some pattern. So this is our test statistic, and this test statistic is now compared with a null distribution, right? In this ratio case, the null distribution was t. In this ratio case, in this plot case, the null distribution is the lineup. Lineup in here where the observed plot is embedded in there. And how we make decision? If observed t, this is our observed t. If observed test statistic is identifiable, then we reject the null hypothesis. So this is how it compares. It's very similar idea to our conventional testing procedure and this visual inference procedure.
You care students. Break. I don't pay. The school pay. So they are paid like. I think they're paid.
Leading their mics.
Okay. So let us see how it works in a real example scenario here. So we have two variables. Variable 1, we call it x1. Variable 2, we call it x2. And we have a response variable, which is y. And variable 2, which is x2, is a categorical variable. Okay? Now we want to test whether there is an interaction between this continuous variable x1 and the categorical variable x2 to explain what is happening with our response y. So that is our goal here. That means we want to test the interaction effect, and the interaction effect is represented by this parameter called beta 3. So our null hypothesis is that beta 3 is 0. There is no interaction. Okay? The alternative hypothesis is no, there is interaction. Okay? That means beta 3 should have some value. Now, when we choose the test statistic in here, what should be our test statistic? Okay, what happens when there is an interaction? When there is an interaction, then the line should be non-parallel, right? So here this is x1 and this is response colored by x2. So if there is no interaction, suppose null hypothesis is true, if there is no interaction, then those lines should be parallel, right? This beta 3, so remove this, turn this into 0, then this should be parallel. That means this plot will serve as a good test statistic. So in this plot, can you identify which one is different? It's 19, right? It's 19. So 19 shows that it is different. Now, I know that 19 was my observed data. You don't know that, right? So I know 19 was my suspect. I arrested 19, right? Now you came in and you said, yes, I found 19. Okay, fine, that matches. So I reject the null hypothesis, okay? Now you may think, okay, that's very intuitive, that's very easy, right? So let me give you an example where null should not be rejected. There is no evidence to reject null. How that plot look like? So this is an example. I know the suspect. I am the police. I arrested that suspect. Now I ask you, can you identify the observed plot in here, or which one is different in your opinion? I mean, I need some response from you just to 2. 3 people are saying 2. Very good. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1 You say 5, 5, 2, and 5. Amazingly, none of those are my arrested plot, my observed plot. My observed plot was number 13. Okay? So as you can see, you have seen some pattern in 2 and 5. But those are generated based on the assumption that null hypothesis is true. That means this pattern that you are seeing looks like they are not parallel, but they are random. I mean, even if you simulate some data with assuming parallelism, still you may see some non-parallelism like that. So this is happening because of the randomness. Okay? The actual plot that I observed in my data is number 13. Now, none of you could identify that observed plot, right? So you went to a police lineup and you pick a police person to be suspect, right? As a policeman, now I decide, I cannot reject the null. I have to bring more evidence. I have to bring more data, right? That should be my decision now, right? I can never say that null is true, right? Police never say null is true. Otherwise, why you suspected the person, right? Arrested the person. So as a police, now I will say I cannot reject the null hypothesis because my evidence, evidence does not support that. So maybe I need more evidence or more data or whatever. So that should be my my decision. So this is the visual inference procedure. Okay. So now let me give you some examples. Okay. Suppose I have a lineup of size m equals 20. So by lineup size, I mean number of plots I have in the lineup. So that I defined by m. Total observer. So we show the lineup to people to observe the lineup and give me the feedback, right? That's called observer. Now in here, suppose you are my k observer, right? I have k people sitting in here. I ask this question to k people. So I have k observer in front of me. And then we fix our type 1 error alpha to be 0.05. That means we say, okay, if we make any mistake like 5%, we are fine with that. Okay? So if null hypothesis is true, suppose null hypothesis is true, here null hypothesis is true, then still you can pick. So some person can pick 13 at random, right? And the probability for accidentally picking that observed plot is 1 over m, right? 1 over m. So if null hypothesis is true, then picking the observed plot, the probability of picking the observed plot is 1 over m. So number of people out of my k people can choose the correct plot is following a binomial distribution. And under null hypothesis, if null hypothesis is true, then the number of people who correctly evaluates the plot is a binomial distribution. For our case, which is 5 over 1 over 20. Okay? Then we can solve this equation. We can solve these equations to obtain the value of correct evaluation for which we will reject the null hypothesis. And we got x alpha has to be bigger than 2. So if 2 or more people pick the actual plot, then we can reject the null hypothesis. If I show it to 5 people, 2 or more people obtain the actual plot, then I can reject. If only one person finds the actual plot, I cannot reject. Okay? So this is how we solve this problem of rejection. Now, you can show it to only one person, like k equals 1. That should also work. If k equals 1, that means if that person could identify, you reject, cannot identify, you fail to reject. Now, when you pick 2 or more or 5 people, like here in the example I pick like 5 people, that brings the power in this test. Okay, so we'll talk about that later. Now, how to compute the p-value in this process? Okay, so we can use this equation to compute the p-value from this binomial distribution. So for example, suppose we have k people in here, so 5 people, lineup size m equals 20, number of successful evaluation x equals 2, we know that already, right? Then p-value, what is the probability that 2 or more people will pick the actual plot? And that probability is 0.0226. If null hypothesis is true, that is the probability that people will correctly pick that. That's a very low probability. So that is an evidence of alternative hypothesis, right? So maybe we should reject the null hypothesis against the null hypothesis. So this is how we can compute the p-value. Now let's talk about the power of this test. So we have actually run several experiments on the known results. For example, we know that f-test and t-test are called uniformly most powerful test because theoretically you cannot obtain more power than f-test and t-test. Those are called UMP test, uniformly most powerful test. So we use those known results for those ideal scenarios of f-test and t-test, and this is how it looks like. So this red line is the power of uniformly most powerful test. Look at the red line here, power of uniformly most powerful test. And then this dotted line is the power of visual inference where k is 1. And then as we increase the number of k is the people who evaluate my lineup. So this is k equals 5, k equals 5. And this is k equals even bigger, 10. So as you can see, as k goes up, our power is going up and up. Not only that, in conventional inferential procedure, what we learn in our classroom is that if you want to increase power, you cannot control. You have to also increase type 1 error. I mean, you cannot do like decrease type 1 error, increase power. That is not possible, right? That's what we have learned from our conventional classroom. You have to control one. You have to fix one. So we fix type 1 error and then try to maximize power. That's what our goal was in conventional testing procedure. But here, look at this plot. Type 1 error. So this is the type 1 error, right? This is the type 1 error is going up, power is going up. Type 1 error is going down as k increases. Type 1 error is going down as k increases, and power is going up. So by bringing in more people in this process, we are actually getting more power of our test. So it beats the uniformly most powerful test, which has been our theoretical result so far in last 100 years, that you cannot beat uniformly most powerful test. But now using visual test, we can beat that power. So let us have some case studies, okay? So we applied this method in several scenarios. So this is one of the scenarios. This is about the pepper wasp. Amy Toth, a Iowa State University faculty, who actually works with wasp genetics. Okay? So she has these 4 types of wasps, pepper wasps, colored by different color in here and letter, right? F, W, Q, and G. And she collected some multidimensional data, like a lot of variables of the data. And then what she did is she did a linear discriminant analysis and computed the first 2 linear discriminant and then plotted this data like this in here and colored them by 4 types of different genetics. And then she was excited. Okay? This is an exciting result, right? That shows that these 4 types of wasps are genetically different. This is exciting. And she was so excited, she published this paper. And this paper is published paper. Okay? And then we took that published paper and we said, okay, let's see how visual inference work in there. So now we have to think, this is our test statistic, right? Now we have to generate a lineup. So how we do lineup? So what does null hypothesis say? Null hypothesis says that all the wasps are genetically same, right? That means I can randomize this color. I can put some red in here. I can put some blue in here. I can put some green in here, right? So I can randomize the color code of the wasp, right? So what we did here is we randomized the color information of the wasp, and then we did that linear discriminant analysis and generated this plot. And we did that many times, right? And then we obtained this lineup. Now I ask you the question. What was the hypothesis here? The hypothesis is that they are genetically different. So if they are genetically different, then if I color code them, then they should be far apart. So my question is, which plot in this lineup shows most separation? I need feedback from you as well. 4, yeah, 4, and then 20, 13. So 4, 20, same thing people are saying online as well, 4, 13, and 20. I agree with you. Those are the plots that shows biggest separation. But remember, those plots are generated randomizing the color structure. So once I randomize the color structure, that means null hypothesis is true. Still we see this separation. Okay? The actual observed plot, this is my observed plot. Where is it? You could not identify it. I showed it to you before, right? I showed it to you before, but you could not identify it in this scenario. And that plot is number 3. Number 3. Can you recognize that? These are all W's. So let me go back. Sorry. So you see those two F in here? Those two F are those two dots in here. Okay? Can you see the similarity now? Now you notice that if null hypothesis is true, it is possible to see that much of separation. Hey, be careful. Even with null hypothesis is true, that much of big separation is possible to see. Now you got this much of separation. You should not reject your null hypothesis. You should not reject your null hypothesis. Now, we search the literature. There is no statistical method to test whether this is significant different or not. There is no statistical test available to test that this separation is significant separation. And we now prove that this method can be used to statistically test this kind of separation. Okay? So, what should be our decision? We should not reject null hypothesis, right? Because you could not identify the suspect in here. Instead, you choose a police person, which is innocent, right? So, as a researcher, we feel like we need to contact her, right? So we contact her, Amy Todd, and we publish another paper now saying that this is the truth. This is happening in here, and this is a nice application of visual inference. So now that's a very good application of visual inference. Another case study, the text data. Okay. Now, if biology is an ocean, then text data is even bigger than that, right? A lot of problems in text data. It's not number. That's another challenge. We cannot just compute test statistic from the text data. So let's see how we can use visual inference in problem of text data analysis, right? So here is an example. So I have a lineup in here. I am asking to you, which text most likely be the part of a traffic direction? 3? Anyone else? 3? 3? Yeah. So out of K people, I already get more than 2, right? More than 2. So our null hypothesis is that the text that I have is not a traffic direction. That's our null hypothesis. Alternative hypothesis is, no, it is a traffic direction. It is part of a traffic direction. Okay? Now we test that, and this is a lineup, and you could identify the suspect that I have arrested because I know it is my observed data, and you don't know which one was my observed data. And you pick number 3, which is correct. So I reject my null hypothesis that it is not a traffic direction. So I have to reject it because you could identify it. Now, what is the significance of it? I mean, now I can compute p-value, I can compute all sorts of things, all sorts of theory now works behind. I know the power of it more than uniformly. I know all sorts of things, like, so this is magic now. So how can I apply these ideas now? Okay. For example, identify hate speech and measure the statistical significance of your identification. Or you identified some hate speech. Okay, fine. What is the p-value for it? I mean, how much confident you are? I mean, p-value tells me how confident you are, right? Now we can compute p-value by saying this is a hate speech. Something like that. So we can now do that in a broad scenario. Test the authenticity of text. For example, a big open question in literature right now. Did this author write this book, right? For example, Shakespeare. Like, people are now saying in one person's life, one person cannot write so many plays, so many good plays, right? So people are suspecting not all plays are written by Shakespeare. I mean, even though people think this is Shakespeare's play, it is not actually Shakespeare's play. So what happened in those days, Shakespeare was a very popular person, and whenever people hear this play is Shakespeare, then people rush in there. So a lot of good writers, like myself or yourself, wrote plays which looks like Shakespeare, and they started playing it as if it is Shakespeare. And then they earned a lot of money. Now, after so many years later, we lost the track, which one is actual Shakespeare and which one is copy Shakespeare, right? That's why we see so many plays in literature for the name of Shakespeare, and which is not possible. One person cannot write so many things in one lifetime. So we can do that. So that literature now can be tested. Let's grab some text from Shakespeare, create some lineup, assuming it is not Shakespeare, and then see if people can identify it. If they can identify, then this literature is Shakespeare. If not, we should reject, right? We should reject or something like that. So these are some other ideas that now opens up. So this creates new area of research now and opens up a lot of door to solve a lot of difficult problems. Okay? Now, why we will be using visual inference? So that is my concern here. First, theoretically proven power, right? Power is more than conventional uniformly most powerful test. It is intuitive. It is intuitive. Why I am in here? Because I know I cannot be overboard by math equation, right? This is very intuitive. A police officer will understand the method very clearly, right? So it is very easy to collaborate with our non-statistician colleagues using this method, right? They will just see it and they will say, oh, I understand what is going on. It's very easy. And it is very easy to teach. I know I learned test of hypothesis in my undergraduate statistics class. I remember how hard it was for me. I did not understood anything. Everything went through above my head. I just mechanically did things and I could do it mechanically. But later, when I came back to my PhD, I realized what is going on in there, right? So why not we use this intuitive method of what does test of hypothesis do, right? So this is very easy, intuitive to teach in classroom. The another benefit is it is non-parametric in nature. That means I'm not using any parametric assumption. No distributional assumption is made on parameters. No regularity condition. I mean, even if you use t-test or f-test, there are some regularity condition, right? Continuity, you cannot do all those integral transformation, all sorts of assumptions are in there in the back end in the theory. If those assumptions does not work, your theory in f-test fails. That is why you cannot go beyond f-test. That is the limitation of f-test that holds you out. That's why you cannot get more power than that because of those conditions that you have in the back end. Now we release all those conditions. We don't have any condition now. So that's why we see this power. That's why this power is boosting right now, because it releases the dam, right? Same thing in here. Because of this flexibility, this method can be applied almost all scenarios. You name a scenario, you can use visual inference in there. Okay? Can be used to verify the results of a conventional test. So suppose you develop a testing procedure, right? You can verify whether your testing procedure is working in reality or not. Use visual inference to bolster your result. You are submitting a report, you are submitting a paper. You use visual inference to bolster your result. Okay? A lot of researchers are now doing that. More than that, this provides us practical significance. There is a thing called statistical significance and practical significance, right? So if you have two whales, suppose you have two whales, one is in Atlantic Ocean, one is in Pacific Ocean, two whales. And one whale is, say, 1 pound more weight than the other whale, right? So the weight difference is 1 pound. I can make that 1 pound difference statistically significant. I will just sample like 1,000 whale, and that 1 pound will be statistically significantly different. You agree with me? So how much do we care with that big two whale where they are different in only 1 pound? How much do we care? How much do we care if two star is different like in 1 ton? 1 ton different. How much do we care? Those are insignificant, but statistically significant because we have billions of stars. That makes those things statistically significant. And this is a new problem in the area of big data. Okay, so I just faced a problem with education department data where they have like 2 million students, and then anything that we want to do is statistically significant, like male-female difference still significant, their ethnicity statistically significant. Everything we collect about the student is statistically significant. Schools are statistically significant. All sorts of, and that doesn't make sense because we care only practical significance that we care in real life. So if there is a difference in 1 pound in newborn babies, then we care for that. That is practical significance. But newborn whale babies, maybe 1 pound, I don't care, right? So this visual statistical inference method provides us practical significance. The practicality comes from the fact that we are using humans in there. So we are going back from automation to human again because humans are more powerful than anything that we use so far. Humans are more powerful than computer. Humans are more powerful than theory. Okay, that's my conclusion in here. So this method works in all scenarios, provides power, provides practical significance over statistical significance, and it works. That is the main thing, and it can be applied in varieties of scenarios. Okay? So that's how we can use the graphics to make that kind of decisions. Okay? So that's my talk today. So if you have any question, I would love to answer at this point. One thing I can add in here, if you are doing research, you are collaborating with other non-statisticians, you feel like you need some way to test hypotheses, to test the significance of the hypothesis, I will recommend that you try it, and then you will see how it works. The only challenge would be to be able to create that null plot. Okay, and that's very easy. I mean, whenever you are testing something, you have a hypothesis which is null, right? And then, assuming null is true, then simulate data. I mean, when null is true, that means I can simulate based on the null, right? If null says something, I can simulate. For example, in police case, null is that null hypothesis is that they are innocent. Then they just grab some innocent people, right? That's their simulation. Grab some innocent people. That's simulated null data. So simulation of null is very easy. So we can put that in there, and we can test the hypothesis. So it works in every scenario. Yes.
Non-statisticians, are there packages? Non-statisticians, are there software packages?
Yes.
Data that can execute this?
Right. So if you want to generate this plot here, there is a package, R package called Nullabor. That Nullabor package will allow you to generate pictures like that. What does this picture do? This picture creates 19 null plots, and then randomly put your observed plot somewhere. Even the researcher will not know where it puts the random plot, the observed plot. So that researcher can make the decision too. So the researcher can be observer in here. It does not bring in other people. So this Nullabor package written in R can generate lineup like that. But in that package, you have to specify how your null will be generated. So once you do that, then this Nullabor package will create this lineup plot for you. And it will randomize the observed plot somewhere in the cloud, and it will give you a code where you have to decode using a R function. Because that code contains the observed location, but you don't know right away where the observed location. You look at the plot, you decide, oh, observed location may be 5, and then you decode it and see whether it is 5 or not. Yes, question.
Yeah, thanks for the presentation. So a few questions. So when you're creating the random pictures, I think the critical part is that how to control the level of the randomness, pairing them with the actual plot. So if it's too random, probably the actual plot will stand out more. So the level of that randomness probably is going to be getting to the decision. How do you kind of formulate that? The second part is I'm still not sure, like, so how do you decide that? I mean, you just find people from somewhere and then, show that. That process, I'm not still sure. The third is, I don't know how you can question. We're relying on statistics because are based on their anecdotes and not scientific and not data driven. So that's why people make wrong decisions. We're kind of arguing that we're going back to that. So I don't the point, but at the same time, then you're kind of going to the subjective impression of data rather than objective testing. So either point, but at the same time, I think.
Okay, so let me address all three of your questions. Your first question was the randomness, right? So, I mean, we have to rely on randomness, right? I mean, randomness can give you the correct answer or can give you a value in the tail, right? So that is the reason we pick not only one plot, we pick like 19 other plot in here. That means if one random is very extreme random, right? It is possible, right? If you have a random number coming from a very tail of the distribution, it is possible. But you have 19 different random sample, and then all 19 of them coming from the tail is very difficult to believe because of the random, right? Why it has all of them would come from the tail. So that solves that problem of these random differences. Okay. So by taking more than one null plot, we use several. So that.
But even there, I mean, you actually do see some pattern in each picture. You know what I mean? If you increase the randomness of the comparison picture, say every other picture is just like a mixture of plots.
Mm-hmm.
Just the one picture has some pattern.
Mm-hmm.
That's going to be very different to making that.
No. So this is, I mean, this picture is not that. I mean, let me tell you how we generate this picture. So we have the original data, right? We have like 500 columns, and then one column contains this is F, this is W, this is, right? And then we randomize that column on that 500 column data. And then we use the linear discriminant analysis based on the color of that column. And each plot is that plot. We did not just randomly color them. If we randomly color this plot, then all the color will be everywhere. This is not what we did. What we did is we randomized the original, I mean, we mess around with the original color of the data. Because original color should be random, I mean, if there is no difference. And then we do the discriminant analysis, and then we plot this. And then this is another randomness, this is another randomness, random separation. So when we have a high dimensional, so this is the problem of high dimensional data. When we have a high dimensional data, you reduce it to a low dimensional space, then you see this kind of issues. So we have to be very careful when we make decision in a low dimensional space when actually we have the high dimensional data. That's what we are saying in here, that we have to be very careful. So your second question was, I think I forgot.
Yeah, the second question is, I wasn't still sure how do you like do that process? Like. Okay,
fine. So how do you do that process? So you generate the lineup and you show it to someone, or you can see it yourself too.
How do you pick someone?
You pick anyone. Okay. Because we also did research on people. So we collected 1,200 people around the world. So in our scientific experiment, we collected 1,200 people around the world with from different countries, from different demographic, different education level, different culture, different language, all sorts of people we did research with, all those 1,200 people. And then we found that no matter what kind of people you pick, the decision-making process is not different. So that is scientifically proven already, that it doesn't matter who you pick. You can ask your 5-year-old daughter, and then if she can pick which one is different, you can rely on that as well. I mean, it doesn't matter what is the age. I mean, we did research on age, we did research on culture, we did research on education level. It doesn't matter. So that paper answers your question, how this will work. And the third question you asked was about, I think this research also answers your third question, right? How other people use that. And the third one is the concern that you have. Okay, now you are coming to the manual system again. The point of doing this is to make things automated. Why you are making it manual again, involving people, right? That becomes manual. Because there are problems that we cannot solve. Because there are things that we do not have test or hypothesis for. This is where this visual inference should be applied. Because you do not have any testing procedure. So you have to do it manually. So when you have to do it manually, you do not have a manual process to do it manually. But we provide the manual process to do it manually. So that's one thing. The other thing is, you do it automatic. So you wrote a program that tests your hypothesis, everything. Everything is done. Now, how do you test the automation, whether automation is working properly? So you pick few automated sample, and then see whether it matches with visual inference, right? I mean, this is what we do, right? In quality control, the process is tested automatically, but it's still manually we go there and take some sample, right? And then we put the manual process, and the manual process applied with the automation, then we agree with the automated process. Same thing will be in here. I mean, we will not completely rely on automated process. We will take visual inference ideas and then apply that and see how well automated process is working. So this procedure will bolster our existing automated process. So that's what we are claiming. We don't want to say that this should be the only method you should be using. This will help us in improving our existing process. Question? Okay. Sure. Mm-hmm.
We have an online question. Are there any resources you recommend to assist in determining what kind of visualization to use for particular data sets, such as the elements of graphing data by William Cleveland?
Okay, so yeah, I mean, we have all sorts of graphics standard in Tufte's principle, Cleveland's graphics ideas. So I actually teach a class at UNO called data visualization, and in that class I talk about how to generate good statistical visualization. Now that statistical visualization can be used in testing procedure, so we have to be very careful how to generate quality picture, how to generate a picture in a way so that there is less mistake in there. So the resources that you are asking could be like Tufte's visualization, like Cleveland's visualization, and other people who work in data visualization. They have nice books. I mean, Tufte wrote a nice book. Cleveland wrote a nice book on data visualization. So those could be nice books to go through to generate effective visualization. Yeah. Mm-hmm. Any other question? Does that answer the question? I am not sure. Okay, yeah. Mm-hmm. Any other question? Okay, thanks. So if you need any collaboration in that area, you think visual inference can be applied, I'm here in town. Just shoot me an email. We can talk. Yeah.
We're over here, I guess.
Yeah.